Okay, so this competition is about landmark retrieval and recognition. So my name is Transitivity Odo, and so the plan is I'll discuss a little bit about myself and the background of these competitions. So there are two competitions in one. They are closely related data sets. So and I would go through some of the winning solutions and go through some of my solutions as I attempted this competition and ran out of computational space on my system. So and then some conclusions. So yeah, I did my grad studies in Saskatchewan and did some research. Right now, I'm looking for a job in data science. So, and I've split in a number of places. So, the landmark retrieval and landmark recognition, one has, if you look at it, they're actually related. It's like in the retrieval case, you have like a query image, and you want to select all images that contain the same object in them. So that object happens to be a landmark. So, and landmark in this context is loosely defined. So sometimes it's a house, sometimes it's some monuments like the Paris, what's it called, this tower in Paris, and like Eiffel Tower. So, and there are many of these kinds of landmarks, and there are 15,000 of them. So it's a lot of different landmarks in this competition. So the goal is to identify the which images has the same landmark. And then the recognition one is identify a landmark in an image. So, and since I looked at the past presentations we've had here, and many people have not worked on information retrieval. They are basically focused on recognitions, CNN recognitions. So I decided, oh, it's also good for something a little bit different, something towards retrieval, and then some part of recognition, since they are both similarly related. So a number of people took attempts that are either supervised or unsupervised, and we discussed them here. Yeah, so in this competition, the first prize, this is actually a research-based competition. So Kaggle hosts these research competitions. So it's like most of the participants in these competitions are actually researchers in some universities. Like the guy who took the first position is a high school student who has published a few papers. And I've read these papers, Mikhail. I actually spoke with him and we exchanged messages. He's a great guy, great guy. So it's like people of different backgrounds, and most of them are in the universities, and some of them are postdocs. Some are like high schoolers who are very, very gifted high schoolers too. So yeah, so on this, the data sets are kind of similar because they are similar distribution of data sets, but there are a little bit differences between them. So, but one has like the retrieval one doesn't have labels in them. So, and the recognition one has labels. So if you look through the images, I didn't see any unique differences between them. So, but somebody in, I think one of the solutions realized there was a difference between them and trained the neural networks to differentiate which images are from different competitions when augmenting the solutions. So, yeah, so this is actually a description of, you have like 1 million training images and some 100,000 testing images, and they are varying resolutions, and it's like 320 gigabytes in total. Yeah, so this is just an example of some of the images. So like actually stole this this from, there's actually a CPVR workshop that, hello, okay.
Hey, I'm just wondering if there's any metadata associated with any of these images?
Yeah, there's some metadata, but actually I didn't, most of the competitors did not use it. So, the winning ones at least. But they actually discussed that you could use it for your solution if you get reasoning out of it, if you can say something. So actually, there's this competition is closely linked with the CPVR workshop. So this is a computer vision workshop. And so one of the slides of those presenting at that workshop, he actually identified these images, so I took it from him. So this is actually one image. Let's say the one on the left-hand side is your query image. The one on, maybe this is a query image. Probably this could be one of the matches from the test data set. So this is just to show you like how some things can be similar. So you have different kind of lightning conditions that are different between the query image and the retrieved images, for instance. So these are like, you see, this is like one part of, this is like the sunset on this building that are on the edges, just like Italian kind of buildings on the edge of the cliff. So, and this is like with sunset. Maybe the sun is on the other side of the place. So it's like, so, and then this is just to show you how this is like a match when you have matches, for instance. But usually you're expected to have like 100 matches. So I will discuss the evaluation metric as precision at, what's it called? Mean average precision. So it's like precision at 100. So, and I'll discuss what that means in a little while. So this is just to show you matches, like images that match. And then I'll show you mismatches and see how so this one on the left-hand side, it's like, this is a house, but this house is not the same as this house. So, but there's a similarity based on colors and roofs. So like this would be like a failing prediction. If you predict this like to be the result of querying with this image. So this would be a failing stuff. So you see these two buildings look very similar. So this is like a failure in terms of what you predicted. And these two look similar too. So it's to show you that despite the fact that the things could look very similar, but they're different images. You see, these images are different airlines actually. So they can't actually be of the same object. So it's like, and then you will see how some of the people participating in this competition started designing their solutions, creating vectors that they call it descriptors, that things like vectors that describe your image, the global descriptor and the local descriptors. So, and you start seeing how.
So some of these images really stretch the definition of landmark, like the airplane on the left. What is the landmark there? Like, so did they just have a bunch of data in there that was kind of like bad data to mix things up?
If you look at the recognition stuff, in the landmark recognition, they have a list of landmarks. So you're given an image, you're not told which object in that image is the landmark. So it's like you're meant to like infer the landmarks as a latent information from that image. So, but when you start observing these images, you can start seeing what they could have meant by landmarks. So, yeah, and again, if you see in the scoring too, they actually did some things I'll discuss when I describe the evaluation metric. So, yeah, so in those contests, those ones that were having like global vectors and local descriptors, as they call it, the global one captures the like an overview of the image, and then the local descriptors captures like regions in the images. So they like the first place solution had a combination of these kind of techniques for building images like vectors with different regions. So and they identify objects and created a vector representing those objects. So and yeah. So this is just one of those. Yeah, and then these are other kind of mismatches too. So a number of the people you doing this competition, a few people use techniques specific to the depth algorithm, like this is capturing the geometry of an object. So I think it's kind of popular in computer visions. Because actually I went to this competition without having a knowledge of computer vision and all those. So it was a steep learning curve. So and luckily in this competition, there are a lot of research papers people are basing their solutions on. So and I actually read all those papers and understood the techniques used. So it's and so I'll be discussing them while I move on, and then I will also like in some of the techniques I used are similar to like using the DFT, the wavelets, and the sensitive hashing concept that I will discuss in future slide. So yeah, so now so this is the Google landmark retrieval. So the evaluation metric. So I actually just copied this out from the website. So this is a mean average precision at 100. So the goal is to identify the 100 images that are most relevant to the query you have. So the query image. So because usually, like when you're doing an information retrieval task, people expect the information, like the results that are most relevant to your queries, to be on the top of your list. So because for instance, if you're searching Google, for instance, about something about SFU Ventures Labs, you want to be shown SFU Ventures Lab buildings. You don't want to be shown the SFU that's over there in Burnaby. So because even though they are similar, it's SFU, but the SFU Ventures Lab in downtown is closer to your needs. So that should be on the top of your list.
And just to be clear, what is the query that you're making? Is it a string?
No, it's an image.
Oh, so it's an image and then you're looking for other images like
Yeah,
that?
like that.
Okay.
So yeah, so your query image, your query is an image. So your goal is to retrieve other images that have same landmarks in them. So let's say same objects in them. So whatever those landmarks are. So if you know, so if you see this metric, what this does, if you see Q is the number of queries depicting landmark in the object. So what that means is you want to take a subset of your data, of the entire data set that is relevant to your information need. So because anything that doesn't have a landmark shouldn't be considered for your, it doesn't make sense to anyone. If there's no landmark in the image, then it's useless for your information need. You shouldn't even return it anyway. So they're actually filtering it out from their storing. And then the number of index image containing, that's the M subscript Q, that are containing the landmark common with the query image Q. So this is just like you're looking for like an intersect of objects between a query image and the retrieved images that you have. So on the list of retrieved images. So yeah, so your model will make like a number of predictions. So that's like NQ for this query. So now if you look at this, because they are actually focused on having a precision at 100. So let's say you trying to, let's describe this now. Okay, let's say you have boxes, like you have different boxes with, maybe you're stacking all the queries, like in a stack. So with the most relevant one, maybe the one on top. So the goal is, if you put something in the wrong position, this value will score you 0. This is like an indicator variable. So this is like, if an object is, if you miss the position in the list, like in your ranked list of objects, and you make a mistake on that, like you put the first object at the second object, you get a 0 score. So, and then this is like how, and then the PQ is like the precision value at that. So at that value, so is, okay, how will I describe that now? So now, for instance, if you predict everything wrongly, if you predict all your scores wrongly, this will remain 0 all through your prediction. So you only need 100 of them. So you don't want, because you only need precision at 100. So anything beyond 100 is useless for your contest. You don't want to like check the query across all the entire images. You just want to get the 100 most relevant image that satisfy the query images that you have provided. So if, for instance, your model gets a prediction that is all wrong, this becomes 0. And then multiplying this by 0 returns everything to 0. So if you're having 0, that means you made your model is predicting everything completely wrong. But if you got everything right, so that means this would be like 1 at all times. This is like an indicator variable. So like that means you get a 1 at the end. So when you take this average, this would be like, this would just be like Q multiple times. And then this would be Q over Q, that would be 1. So the best result is 1, and the worst result is 0. But in this competition, the best solution is 0.25. So, and that was a good one. Do you have any question about this metric? Okay.
Sorry. Okay, so I understood the relevance, but could you go over the P, capital P value, the precision?
Yeah, so I was trying to describe what precision is. So I actually checked the dictionary meaning of it. So, it's what I put up here. So they said like it's the fraction of the result of a query that is relevant to the information need. So then I was imagining how could they have done it. So maybe they have a list of different positions where objects are, and they're checking which ones are relevant to that position. So that's how I think they may have done it at the back end when storing it. So I looked at the dictionary meaning of precision, and that was what it showed me. So yeah, and then the submission format is this is your query image. This is the ID of your query image, and you now have a long string of all the retrieved images on the side. So you stop at 100. So the 100 was relevant. So if you see there's a minimum, actually there's a minimum of the number of Q to 100. So you don't have to be 100 actually. So if you have like 60 most relevant, you could return that one instead of the minimum value. So if those are the ones that have landmarks that are common between your query images and your retrieved images, you don't have to bring up 100 irrelevant stuff. So you stop at the minimum you have.
Can you just send in your one image that? It's not clear what stops you from just sending in the one image that you have the most confidence in.
Yeah, you
And
can do
then
that.
because the relevance will then be high and I guess the precision becomes low. Can you go back to the definition of precision? Yeah. Is it a good strategy to just send in a very small number? For each ID?
If you send a very small number for each ID, you will still be penalized because if the query image and this list of your return image should have common landmarks. So they will score you with all the common landmarks. So you're already at a discount for those other values you had misperated. So you're getting a score of zeros for those parts. So yeah. So you could do that, but there's a scoring loss you incur as a result of that.
There are multiple matches to your query image. If there are multiple matches to your query image, so say that landmark is represented multiple times in the search set, if we go back to that formula, then the denominator of MQ increases and lowers your precision, or lowers your overall mean precision. So just in the middle of the formula, underscore min, like MQ, so MQ, number of index images containing a landmark in common with the query image, right? So if they have multiple images that actually contain that same landmark and you return just one, your overall score decreases, if I'm reading that right.
Yeah. Okay. Yeah, so we now know how this submission file looks. Oh, okay, someone else has a question.
Quick one, where are the images from?
There are some URLs provided. I can't actually remember. I think it's Google Landmarks. So Google has those images. So they provided URLs.
People uploaded them to Google.
Google provided a list of URLs in the CSV files. So you have to write a script to load those.
No, I mean literally, where are the images from? Are they holiday makers uploading their photos, or what is it?
I don't know about that. I didn't check about that. Okay. Yeah, so now we go back to information retrieval. So I decided, so I just want to represent it in mathematical notation because I'm not a mathematician though. So there'll be slacky notations, so just bear with me. So it's like you're giving an image V. So that's your query image. You're giving a query image V. So and a collection of all the images in your test set. So in our context, your query images will be the test set. And then your what's it called? The total retrieved images will be the sets of all your training objects. So on each of the test sets, that will be the submission folder that you saw on the other slide. So that will be the ID, the hash ID, the UUID of that image. So now if you have this, the collection of images, that is your test set, for instance, and you have just one image. So your goal is to return a set of images that are most similar to V. So that's what this is trying to do. This is just a union. I'm just trying to say a union of taking all the elements of your test set and checking the similarity between it and your query object, and seeing if it's within your threshold, whatever threshold you have. This is just a mathematical concept to get it clearer. And then we return it here. So you're taking the union of unions of all the images. And then your goal is now to define what similarity is. So what I defined it as, this is the distance between image U1 used as a proxy for the number of common landmarks between them. So you have any question about this? Okay, it's clear then. Yeah, so, okay, yeah.
So just like, do you have like a label that you could show for the training set? Like, is it possible to have, say, multiple landmarks in a single image?
Yeah, it's possible.
Okay, is it also possible to have 0 landmarks in an image?
Yeah, it's possible. So I actually discuss both. So if you see when, if you see actually something like query expansion, so I've not really gone on there. So it's like an image could have multiple, like you see one image like a landmark A has image B in it, and the landmark B has C in it. So you could make some inference of transitivity, for instance, to do query expansion. So yeah, so they have most of those concepts are actually there. So actually, then I did a summary of what people. I don't want to. Okay. Oh, okay. Okay. So you can represent images as vectors. What most people did actually, they represented images as vectors as they should do. So and then those vectors could be these descriptors. Some are local and some are global. And then they built an efficient searching and querying of these images. So they built a kind of structure for querying those images. And a lot of people, because on the average, everybody was at 57, 55 to 57, most of the competitors. So the difference between the people who took the first position was query expansion. So that's when you put in like, you wanna expand your queries. Like, okay, A contains B and B contains C. So then that means A contains C. So it's like you're trying to expand your, yeah. So most people use actually a concept known as diffusion. So I actually read to this paper. I think you should also read it when you get home. So this is a very nice paper. It's actually describing a way you could do that. So, and it actually made reference to, so it's an iterative algorithm where you actually specify what's it called, distance matrix, a pairwise distance matrix of all the images you have, based on the metric of the distance vectors you have. So you have a pairwise of them, and then you multiply them with an identity matrix and do what there's. It looks a little bit by similar value decomposition, but it's not that. So it's like you want to convert that into a transition matrix to represent each of the object as a state. So actually, when you look at that paper, you should see all the concepts in use and then how they did iteration so that they avoided having this kind of inversion matrix with negative, with inverting a matrix and making it efficient. So yeah, so this we can actually discuss this over beer or coffee. So that would be, so I don't wanna bias the concept of this talk because that's pretty involved too. So then the descriptors actually just a way to encode an image in a vector that allows comparisons between images. So and most of the people had a kind of a combination of a kind of a global matrix of the image. So this is what you get like if you use a pre-trained network and chop off the edge before you spit out the labels. You just chop up at that point. What vectors you get in there actually captures a kind of a global view. So, but then the local descriptors, they had a combination of regions in this object, and they have a vector of all the regions. So it's similar to what you have like in your fast RCNN. If you've read that paper before, it's so it's like you're trying to propose regions in your object. So you want to figure out where the objects are in the images, and then a vector representation for all those objects. and then have a way of aggregating it at the end to give you a vector that captures all the local objects in that image. So we've discussed a lot of local descriptors because actually the first place solution actually invented a new technique that he hasn't published yet. So, and that gave him the highest score. So in that concept, but the other papers too that we refer to. So this is the summary of what he has done. So, and in this competition, I realized that Keras is not enough for competition. You need something like PyTorch. So I realized now, because I was thinking, oh, I could get around with Keras, but there are some tweaks you may want to make, and it's so difficult if you want to use Keras. So I think PyTorch is something I am, it's like NumPy, so it's easier to understand. So, and then what this guy did is just, I can just give you an overview and then go to the next slide, discuss in details. So he actually used a RESTnet encoding. And then these are aggregation techniques. So these are actually, he was trying to achieve these local descriptors, the local descriptors from this object. And then figure out the way of getting the concatenated longer vectors, perform this video on it, build a kind of k nearest neighbor distance, kind of a distance matrix. So you can find nearest neighbors in that problem space. And then at the end, because he wants to increase the number of matches, he now did query expansion. So that's just this database augmentation and query expansion. I don't know, because I look at the papers and they're similar. So I don't know what's the difference. Maybe there's something, because this part of his model was actually classified. So I didn't know what he did there. Even though I spoke with him, he only referred me to one paper. So I just read that paper. So.
Okay, a couple things. So the blue and green, let's say 3-in, Remap, RMAC, are these different architectures for segmentation?
These are actually, what's it called? Aggregation methods of getting a local descriptor of an image. So it's like you're trying to get all the regions inside this image and then summarizing those regions into a vector, one vector that captures all those regions that has objects in that image. So that you can actually compare two images based on the objects in them. Okay. So, and then they said they actually captured this property of local, what's it called, location invariance, like what's it called? Yeah, location invariance. Right. So, yeah, and then because they also want to capture hierarchical kind of relations in that regions. So it's just beyond the bag of word model. So if you look at all the papers discussing that, they begin with the bag of word model and then discuss the limitations of those methods before moving forward to this. So, and then in the next page, you see the papers.
Sorry, just one more question. Those percentages, are those like the results of some sort of ablation study or something?
So what he did is he tried only this one and without any query expansion, just did this KNN search result alone with this. And he got 30%, like 0.3 if you use the scores. Then he used only this one. And then he got this scores. So this Remap is actually a method he invented that he hasn't published yet. So I asked for the paper. He said it will be out in the week or two. So you should wait for it when it's out. So, and this is actually a new architecture by Facebook. It's actually in PyTorch. So a lot of good stuff in PyTorch. So yeah. So and then what he did was he used some inference from the weight, so which I will call leaderboard probing, and did a kind of a weighted concatenation of these vectors. So it's just about capturing different information from this data. So, and yeah, so then, okay, let me move. So that was what he just did. This lightening stuff and whitening stuff is actually at the last layer. They do it on this last layer. So when I was reading through his solution, there's no way you can just do an L2 number on one vector. You will not get a scalar, but since it's still a vector, that means because the last layers of all these methods have this L2 stuff in it and whitening in them. So I was reading through the paper, so maybe I don't know why he's writing it that way in his description. Is he trying to confuse me or I don't know? So Yeah, so then getting these magic numbers, as they call it, he used the idea from what scores he was getting. So which ones were giving him more prediction, he gave it more weight, and then concatenated into a beta vector and performed SVG. And the PCA, so reduced it to a lower dimension. So and then about 4,000 vectors, 4,000 sized vectors or so. Yeah, and then he went with a simple, an efficient way to match those using like k nearest neighbors. So, yeah. Aha, I remember now the data set documentation. Yeah, this is just more like enriching. I think it's like you take an object and take all the nearest neighbors from it and put a weighted relationship from the neighbors and update this vector you have. So it's like you're trying to increase the information on the particular object using all the neighboring objects in your space. So that's then do you have a question on this? So it's like you're taking like the 10 nearest objects to an image and combining this weight using this scale. It's like this is between 0 and 0.1. I don't know why you could use anything, just anything that can capture the weight. So this is like there's 10 interval of numbers between these two, or floats. So, and then use it as weight to enrich each of them. I think it was done on the test. Where should it be done? It should be on the test. So, no, training. It should be on the training. I think it should be on the training. So then you have an enriched vector representation for each of the training vectors. So you have a question?
Oh man, I gotta think about it.
Yeah, it should be on the training set. Yeah? So actually, this took me a while to figure it out, but if you figure it out, it's not complex. It's pretty straightforward. So, because I was actually spoke a lot with the guy and asked him a few questions. So it's straightforward. So you have any questions? So
Okay, so for this augmentation part here,
Yeah.
you have all the original images,
Yes.
right?
Yeah.
And then what you do to each image, so
Yeah.
you're essentially doubling your image size.
No, you're not doubling it. On one training image,
Right,
you get like 10 nearest neighbors to it
right.
and use those weighted combination, add it on that one image that you have.
Right, and so
So it's like
you could use
information
that
from the
as
neighbors.
the augmentation, right?
Yeah,
So
that's
you could
augmentation.
theoretically do it to all of,
All the training set with their nearest neighbors.
what kind of blows my mind here is, aren't those nearest neighbors decided by your already like decent but not amazing, yeah, so they get to this database augmentation, so at
So
this
if you
point,
see-
he's at 47.2%.
Yeah, but then when he did this, you see this, the boost. This was massive. You see it.
Yeah,
In Kaggle wise.
so it's some sort of semi-supervised technique. It just
Yeah,
seems kind of
semi-supervised.
crazy that you can just take the 10 nearest things that are what you're trying to find and then get, a boost of almost 10%.
No, it's not crazy. Actually, I actually read through some information retrieval literature, and people are doing that also in test. Those are years ago. So actually reading through, and they say it's like maybe it has a different name then, but people are doing something similar in the literature. So I had these questions that you have too, but yeah.
To me, this reminds me of Smote. I'm not sure if you're familiar with this, but if you want to generate a bunch of synthetic data, you take the data that you have and generate data that's between it. So it's just, generating synthetic data.
Yeah, you're not
similar to
generating
Smote.
data actually.
Sorry?
You are enriching the data you have. It's more of an enrichment. So you're using the information from the nearest neighbors to enrich each
But
training
you're
example.
adding new examples to the algorithm, right?
Yeah, each of the one by one. So you're enriching each based on the 10 nearest neighbors. So that means it worked if it gave you this amount of boost. So it's a valid method. So, and then this query of this is using transitivity. It's like you have, if an object has an object A, and an object A has another object B, an object B has object C. So by transitivity, then A has an object C. So now what you're doing is like you're going into your problem manifold. If you go back to that diffusion paper, And if you read, there was a vector of the scores. If you look at that algorithm there, and then there's this vector of the transition matrix, you're multiplying it with some weights, and then you continue with a number of iterations until you have this convergence. So you can look at the scores, which of the items are having the highest scores. So you can add those items to your return based on your query you have. So there's an indicator variable too in those query expansion paper. The one I showed you in the beginning. So that's this paper. So this paper, it describes this algorithm and it's very clear there. So you can actually use those scores to retrieve those extra items. So you're enriching your number of retrieved objects based on the current object you have. So the assumption is like, actually, PageRank is actually a diffusion method, actually, PageRank. So it's like the most important information will go through the most important nodes. So the information will flow that route. So it's like the way they say it, they say it's a manifold, and information is going across. So you should read this paper, and we can discuss it during beer, actually. So then, yeah, so this was the party, because he was actually working on this project as a grant for the British government. So, and yeah, it was sponsored by the British government. So I think that's why they had that part classified, I don't know. So those other things that didn't work. So this one is much more straightforward. So yeah, this is just a RESTnet 100. So it's a model and it gets you some sets of vectors. And then you do what they call generalized mean pooling. So you're used to match pooling. But match pooling has its advantages and disadvantages. So match pooling, you're making the assumption that in all the activations you have, you're only choosing the most important one in those regions of activations. So, and it's part of dimensionality reduction though. So that means you're only concerned about the highest value, that there's the most significant activations. But when you have a mean pooling, you're actually taking all the values. So it's like extreme values in those activations will be captured. So it's like you're trying to capture a kind of behavior, a general behavior of this. So it's like actually a way of capturing the global vectors. So global interaction of all these activations. So that's what this I did. And then added the full connected layer at the end. And then did the Euclidean search in a kind of okay.
So, I mean, is that with 15,000 classes? Is that what they, I mean, they're like fully
this,
connected layer to do, I mean, so what they did here with this like fully connected layer at the end in the dash box, learned end-to-end on Google Landmark Recognition training set, is that like classifying 15,000 images?
Actually, I didn't think about that at the beginning.
Sorry, but 15,000 classes? I mean,
Yeah, actually, I should have checked that. So
Okay.
I actually put up the link. So because I think he didn't share his code, so I think it's just this picture he put up. So I think so. I can't remember what he did anymore. That concept. So because in Meetup there were no labels. So yeah, it's a good question to ask. I didn't really think about that. So you don't actually need the labels. So actually, if you go to this place, you can get some vectors that represent each of the images. So there's no label there. This is like unsupervised. You only want to get this vector representation, and that's why you're doing this what you call this generalized mean pooling. So they're trying to the activation spread across each region. So you're getting a global view. So and yeah, so that's what it is. This part will still return a vector set of vectors at the end. So maybe I don't know what it was training towards. Maybe it chopped off the pre-trained network and took this part out. So I think that's what most likely he must have done. So and then these yeah, Euclidean search on the KNN. So just of K nearest neighbor. I mean. And then he did the PCA with whitening and shrinkage. So I actually looked up this PCA with shrinkage. And actually, I didn't understand what those papers were describing. So, but I think it's just adding some extra penalties, so some loss function. So it doesn't look complex. So, but I didn't have enough time to look. The papers were too many, so I just so it wasn't important. But this is what he did. And then the diffusion part is this augmentation I was describing to you. where you wanna take the transitivity relationships and other stuff. So the 11th place, this was the ideas that I should have used because this would have worked on my system because I have more resources than this guy. So, and I was unable to reason properly in this competition. So this is still part of those region marks. So I just built a vector space and then did some data side augmentation. So there's this library that I used. So this library is like a kind of very inaccurate TNN, but very efficient. You have less memory space. So that's why I like this solution. It uses the least amount of resources, and see, it was able to do things quickly. So he shouldn't have. I wouldn't have had the issues I had in these conditions if I tried this. So this is a very simple method that gave him 11th place. So that's why I really love this solution. So you have any question? Yeah, so my solution. So what I was trying to do then, so I was trying to create a number of hashes, binary hashes of 64 bits, and then measure similarities using Hamming distance. And and then I was inspired by an article on Ocpid, this dating site. So they had a way of figuring out when images were distorted and see when there's a match. So yeah, and then you have a threshold to remove unnecessary stuff and pairwise comparison. So this was where I had my problem. So this pairwise comparison. So if I had replaced this with a k nearest neighbor, I won't have the problem I had. So this was a mistake I did. So, and it was so bad. So I wasn't able to think properly in that competition. So yeah, so then I released my code on this part of. So this is just, yeah, it's just I was just trying to use kind of what's it called, a heap. So I don't want to waste my time sorting. So just load things up, go through it. So this was a tight loop. This was a tight loop that nailed me. So that if I have a question.
In terms of the hash, like, I mean, in what way did you expect it to be meaningful? Like those 64 bits?
Yeah, it's in the next slide I will be discussing it. So it's it's coming. So this is the hard loop that dealt with me in the competition, and then so the code is very I just made things a little bit easy with it, some ways of kind of assembling different hashes in use. So so this was the set of hashes I'd used. So it's like if you have an image, you scale it to some fixed size, convert to grayscale. You want to throw out some image, some information, downsample a little bit, compute an average or median, threshold with those medians you have. So this works for images. If you tweak, so this you get a kind of unique. With Hamming distance, it is the amount of steps you take to convert one string into another string. So Hamming distance is a reasonable metric. So yeah, this makes sense, and they used it in Ocpid, so it should work. So and then similar concept, those different kind of hashes. So this was now based on the discrete Fourier transforms.
So was OkCupid principally looking for like duplicate images?
Yeah, duplicate
very
images.
near duplicates? Yeah.
Duplicate images. So that's what we are looking for. So this is a similar concept. So you could use multiple techniques like this Fourier transform, the wavelets, and those concepts to see if you can have multiple images. So, and then the wavelet is, so I actually use also a wavelet. The good thing is, if you look at an image, the most informative part of the image is at the point of gradient, when you have a gradient change. So that's where maybe two objects of different, like two objects. So that's like between maybe this black and this part, is already a different gradient. So those are the most informative parts. So your eye goes to those contours of your image. So those are where the most information are. So if you have like a wavelet and you're taking the high frequency part, so those captures those kind of spikes more. So that's why I use this part to capture those kind of relationship which would be the lower frequency stuff are actually not so important when a human looks at an image. So yeah, so this was the concept. Yeah, then I went to local sensitive hashing. So a hash is just a one-way function. You can't touch. It's just one way. You can't actually retrieve the original results from the representation you currently have. So and if in cryptography, your goal for an hash is to make it as different as possible. So minor changes will give you the total dependent number, so like MD5, for instance. So, but localized sensitive hashing, you want to hash them to be similar. So you want to cluster them while hashing. So it's like, so that kind of a concept. So, and you can look at that, some of those stuff there. Yeah, so, yeah, and if you look at this, there's this book, this Stanford book, Mining Massive Data Set. So I think you must have heard about that book. So I put it, that's the last reference I have in my slides. So, yeah, so it's, you should look that up. So then, after having those hashes that I had, so what came to my mind was to use tries in that competition. So and I would, and still I had memory issues. So and so I would explain how the tries should work. And also I was also thinking of if I could use a kind of a clustering where I just have the position as a function and the object there as a value to create a function that I have a modulus operation that kind of a hash value that gives me unique values, so I can see which objects are sorted in the same bins. But I realized that's not what the problem is asking me to do. I'm not asked to organize images in bins. So, and then that idea failed too. So I was also trying to exploit triangle inequality. So like you have a kind of, okay, you have all those images, then you have like a kind of a common image, like let's say 1 or 2. So, and you want to say, okay, you in your database, you want to have all the distance to that common representation. So you have those values down all the way. So if you want to compare your current query image to that common vector. So because if the rules of triangle inequality hold, as it is in Hamming distance, the distance, if you have a triangle, the distance from A to B plus B to C should be less than or equal to the length of A to C. So I actually thought of that. But then I realized, oh, that will only work if I'm giving only one image and told to return the matches for that image. So that idea also crashed. So I had some job interviews and was angry with the competition. So I have a question.
No, I was going to say, like, I think what you're getting at there with the triangles has got to be related to the diffusion, right? I mean, when we're doing the diffusion, we're sort of saying that we don't kind of trust this basic distance metric and we want to check our neighbors' neighbors.
Yeah, that was when
So
you're
you're getting at the same
but
thing,
I'm
I think.
not actually, I'm not actually doing the augmentation there. I didn't even know that existed at that time. So I actually saw database augmentation after the competition ended, and I saw the diffusion and other stuff. So I didn't know those before. so and at this point I was so angry, and then I was planning to stop the competition. Yeah, the tries was a very promising technique. So what the tries is like, okay, you have for instance, you have a bit like 110 or one number like that. So it's like, okay, if you moving from a root to this tree, it's like T0. So this is like T0, for instance. So if you want to get all the elements starting with T, you can just take all this part. So the goal is I could actually have a representation where I would go with the number of bits down the tree. So then if I have a query image, I can just take maybe first 16 bits, and then from first beginning, I'm going to go and capture all that is underneath it, and then return those most with the score with the most relevant ones that are 10, like 100 of them. So then throw the relevant ones. So this was a promising idea that should have worked, and then I ran out of memory space.
So I'm trying to get an intuition of why a try would work here. So So, I know that try is very useful in when you are looking up a word in a dictionary. It's a very fast data structure, and the reason it works here is that there is the vicinity of characters has a meaning. Right?
Yeah.
So, Ted here, that these two letters they mean something. So I'm trying to understand how this applies to your context. So are you saying that when you hash a picture and there is, let's say, an object, let's say a dog in the picture,
Yeah.
are you saying that if there's another picture and there's a dog in that, you are going to end up with the same substring in both strings?
No, this context is not getting me an exact kind of object matching. So I'm just trying to take all the properties, other properties in the object. Maybe it could be a color of the house or something. So this won't be so accurate either. So because, the competitions like this are research based. So the goal is to have the submission and then start building from there. That's what you do when you go to a competition. You want to make a submission first. So, because actually, those positions have spatial information in them. So if you have done a hash that way, and similar objects will hash to similar strings. So that the Hamming distance between one to the other should be as less as possible. You have a question?
So, but in this data structure, you're looking at the first element of
The
what
query
would be the
image.
hash, right?
Yes.
So wouldn't that mean that you would lose out on, say you have a 64-bit character or bit string,
Yeah.
and the last 32 bits all agree, but the first 32 don't really. Like, you would lose out
you
on
lose
that.
those ones. Yeah.
So would you flip them as well, and you would have two tries, one for essentially the suffix and one for their prefix of the hashes?
That's one design. In Kaggle competitions, what wins are ideas that you see that seems very, very silly. That's what wins in competitions. So that's why when you're in a competition, if an idea that's silly, come and try it. So you don't know, you see people trying different things. So that could work. But I was just trying to make one submission with the resources I had, trying to optimize memory first. And then maybe I would have thought of going down the other route too. And so that was my kind of diffusion. So probably, but I didn't know what diffusion was at this point. So then I went to Fourier transforms. So Fourier transforms it's one of the revolutionary stuff. So it means the implication of Fourier transform is every curve can be represented by a series of weighted trigonometry functions or signs, as they call them. So if you have any signal, so even though I am periodic or aperiodic ones, so you could actually get that way. So let's say we have an object that comes with this equation here. So you want to get a representation of a vector. So these are like the weights. So if you're converting back into the what's it called, the frequency domain. So because you have a time domain and a frequency domain. So the frequency domain is actually this set of amplitudes. So this is like the weight you put on this trigonometric function that you're adding. So so it's like if you have these equations, if maybe you sampled at different points on this equation that is fictitious, for instance. So maybe you say at point 0 you sampled, you put in some angles and sampled from that point, sampled from this point. So you're trying to have a representation. So you now have your amplitude, let's say the weights of your trigonometric functions, and this is like the end of a basis vector. So you could actually, this object may capture some information that you may not be able to see from this. But there's a clause called the Parseval theory that said the energy captured in this is equivalent to what's here. But there's some information that you can actually find in this frequency domain that you won't find in this one. For instance, if you're doing a time series, you want to get where periodicity happens. So you get the spikes in this kind of rotation. So, and then if you take an inverse of this one. So this basis vector depends on how you want to design it. So a few people impose what's called orthogonality constraint on it. So if you do that, you'll be having so if you make a transpose, it become an inverse. So you want to save You don't want to do an inverse. So you may put a constraint on what this basis vector should be when you turn it. Then if you do like the fast Fourier transforms, you may want to exploit what this symmetry of a trigonometric function. So because it repeats. So you exploit it, so you only do one part and then take the other part with dynamic programming. So it's, okay.
Sorry, so this is being applied to the hash, not the image itself, right?
No, it applies to the images.
Oh, okay.
Yeah, so in that case, to be a 2D, you can have multiple dimensions. So to be a 2D, so I just want to be a 2D image. So then if you go to how they write it in textbook, so I don't want to just confuse, I want to use one example that looks a bit similar, something like the fast AI technique, where you start with the example and go to the theory. So this is like, this is your signals. So, and this is like some vectors you're multiplying with this. So, and you get this representation. So, this is your frequency domain. So, that you want to convert back, you now have to multiply them by this too. So, these are actually equations. Because if you don't want to be writing complex numbers, like some basis vector. A basis vector actually, if from Cartesian plane, a basis vector would be like your x and y coordinates from where you orient all your dimensions. So it's like, okay, you have like x, y. So you can actually start placing things on your space in relation to these two basis vectors. So that's what a basis vector is. It's just like, let us say this is actually the foundation or the building block, the fundamental vectors spaces. So you can actually start from there to orient all your problem in space. So I just want to give like an high-level overview. So actually, there's actually a book I referenced at the end of this. It's like, what's it called? Fourier series made easy. I think the URL is at the back of the reference slide. So, do you have any question on this? Okay, so wavelet actually goes a step further. So because usually when you put in a Fourier transform, when you represent things in the frequency domain, you lose the information from the time domain due to what they call Heisenberg uncertainty principle. So where you say you cannot measure one article accurately and the other at the same time. So yeah, so but in this context, so the trick they did here is they just used a kind of a function and move it with you set it a way of scaling it. If you scale that function and make a convolution across your time domain, with the scale value. The scaling value is actually where you set your frequency. So you can actually tune the scale, and that's where you change your frequency back and forth. So and then you generate what they call coefficients. So it's now you have an idea of what the frequency is in that time domain still. So you're having two information, although you lose some information, but you still have both in some context within some slackness value. So yeah, so and then wavelet actually, because of the ability for you to tune these frequencies with the scale, you can actually choose which part of the spectrum to keep and which part to throw away. So it's and it's used a lot in those kind of. For instance, you want to have multiple resolution images, you can actually have different ways of tuning it. So yeah, so I actually gave some examples on. So, but you don't have to read the slides. They verbally you have to explain it. So rather than just reading through. So there are different designs of wavelets. So they all have their properties. So based on what you're trying to capture. So these are actually what you have as, this is like the basis vector. You take and convolve it across your problem space. Then the way you convolve it, there are techniques they try to avoid disobeying Nyquist criteria, so they don't have anti-aliasing. So how you do that so that you don't, when you move across the slides. So yeah, so these are some styles. So yeah, so it's so now you have multiple scales and time domain. So this is just like you can actually tune the scales. With changing the scales, you're changing the frequency. So that means you have a control of the frequency and the time domain based on the coefficient you have. So that what makes it very, very convenient. So you can have multiple scales, multiple frequencies. You can represent those in one in one good representation. So for instance, if you have a large scale, you have a lower frequency, but if you have a smaller scale, you have a higher frequency. So for instance, if you want to capture those changes, like gradient changes in images, so you're better off using higher frequency, because then those spikes will be captured better, because that's where the information is in an image. That's on the edges between one image and the other, how the gradient flows, as they say it. Yeah, this is just one example of how some of those equations. And there are some, what they call admission constraints, where you say integrate the sinusoidal. So there are many of maths. Those maths are not there to confuse people, but because I'm not a mathematician. But those are very easy to understand, because it just says it's you integrate it from infinity to negative infinity, it goes to 0. And then they say the power spectrum less than, I've forgotten the value. So there are two conditions this function should have. So you can design any function you like if you obey those two criteria. Admissibility, constraint, I don't know what the name is anymore. So this is just like that basis function we had shown before. So you're just convolving, you're just moving this across. This is the input you have with time. So this is the coefficient you get if you convolve it. But now I'll also show you the discrete version. Because the discrete version makes it, you see, so then there's a little trick they use using powers of 2, so that they can actually, there's an optimization they added for the fast Fourier transforms, where you have like a band pass field. So there's a little tweak there. So this is just a normalization value. So this is like a shift. This is the shift, how you moving your basis vector as you convolve. And this is the scale you have. So this is the forward part. So you get these coefficients. Then from the coefficients, you can get back the frequency too. So by actually doing another convolution this way, backwards. So, but if you go to the discrete one, because in integrals, I'm not a mathematician too, but integrals are just summation. It's just summation. So this is now clear.
Just what does the star mean? Inverse? Okay.
What did I do? Yeah, I think it's inverse.
Complex conjugate? Yes.
Yeah, conjugate stuff. Yeah, it's the inverse. Or conjugate stuff. So now with the summation, so you can actually go this route and get those values out. So you can see the JK, you passed it in the form of basis vector, and you go back and forth. So you can actually, with the scales, you can choose which frequency part you want. So, and then if you look at the textbook and other books, they had a way of making these shifts using some powers of 2, so they can make an optimization for the fast Fourier transforms. And so, but you're most likely going to use a library too. So I just want to show you the internals, and just get an idea. So this is like, maybe if you're trying to shift, let's say you're convolving on this. This is your basis vector, you're moving it across. So you're moving it this way, for instance. And then this one is like, you have a signal here. You have a kind of a bandpass filter. So but then they said you should take these two values out to in a way that you don't disobey Nyquist criteria, where so you don't have anti-aliasing. So and then you can actually be going down as your state reduces. So if your state is like this, you're not considering anything up there. So this is an optimization for the fast wavelet algorithm. So if your scale is like, you want to use like 1/6 of the original scale, you don't want to consider something higher, because that's not where your problem space is more likely. This is just like a binary tree almost. So you're better off just ignoring those parts and then convolving to the part you want. So so this is actually some implementation. Many libraries will we'll be using this description more is as a fast one. Yeah.
So the low pass, does it go on infinitely, or do you have to define where it's going to stop?
These scales have, there's a way they are chosen. So I think it's powers of 2, or I can't remember. So so at some point, so you just, there's a limit. I don't want to clutter this with so many math equations. So then, in this competition, then after I had those issues, I now decided, okay, then I met Steve and Justin. So they said they had some computers. So I said, okay, why can't we train our models for the landmark recognition project and get a model out, save it in its native format, in Keras or whatever method, and then run our entire training set and test set through it. So we can do, we can actually have a lower space embedding where we can actually do some kind of thresholding, because we believe that's lower dimensional representation of our data in the numbers of one hot encoded landmarks that we're predicting for each of them. Each column will be like all the elements containing that label for that column. So if we make a prediction on a test set, we get the value, we can check the maximum value and add some thresholds to that current value we have to the left and to the right, and query our entire one-hot encoding space and select all those elements that are within that interval. So I did a lot to explain here, and then because it may sound like a bit like a little bit confusing, but then the code is actually very easy once you see the code. So then what is there is like, when you run through your landmark recognition competition, you want to optimize it as much as possible for that competition, because it's the similar landmarks that you're trying to track in both places. So you optimize that as possible, then save the model. Then load this model, and then pass input of your entire data you have through the model and get predictions. So you are getting like a one-hot encoded vector of your inputs you've passed. So what we're trying to do is like, we want to exploit this lower dimension, lower dimensional representation of each of these one-hot encoded labels, capturing each of the images, so which one they belong to. And then we've made the assumption that each column of that vector space is for all the images that contain that label. So those are the ones that have the most significant value in each column of our vector. So this idea actually came from Justin when I was discussing over beer with him. So, and then I did a lot of modification to the idea. And then, so yeah, you can now use it for like, then we have this lower embedding of the hot encoded matrix. We can now use that for our purpose. So in what this is like, each column taken as the list of images containing the label, containing that label. You understand that's what the output from a neural network is usually a one-hot encoded vectors where the maximum value is actually what you're predicting. So then we query, okay, when you run a test set in, so you do this on all the training sets. So you pass the training set into this model and get a representation of all the vectors. So now your training set is a one-hot encoded vector now. So what you have is a one-hot encoded vector. Matrix, not vectors. I mean vectors, list of vectors for each of the item in your training set. So now what you do is like when you have your test set, you pass it through that same model and get another one-hot encoded vector. So what you do on that position, what you do is you take the maximum value of that one-hot encoded stuff you have, and then the position, that will be the landmark it contains. For in this context, is the landmark it contains, and then that landmark it contains, You now go to your training set on that position, add some thresholds to the value you current, and then do a query on that. So with the value you have there, so the goal is all those items you are catching in that lower embedding, as we call it, is actually those that match the test object. So then, I think but then I had another problem. That one not encoding or encoding was too much to fit in my computer, so I also ran out of memory space after trying that. So then I'll go to the code to describe what I did. Oh, okay. Okay, you can read up this. Okay, yeah, yeah, it's all there, so you can read it up. So the recognition stuff is just the number of prediction returned on all queries. So so this is the number of queries. It is similar to what you currently have, but you're taking out the other part. So it's still the lower. This is if you move to the recognition competition, where we also tried to work on. So then this is like the same contest we already had before. So 0 will be when you recognize all the images, and 1 will be when you got everything right. So this is so you're predicting a landmark and the confidence you have that that's a landmark. So that's what you're predicting. So they use similar concept. So yeah, this guy's actually his solution also has another PDF. I think this. So he did a kind of the generalized pooling similar to the one we already had before, and then normalize this vector space. And then these two papers are actually capturing what's it called, geometry of objects. So that's what the Delph paper and the ASMT paper does. So he's using the geometric information as part of his input. So you can check the URL, and we can discuss that over coffee too. So, and then the fourth place, use the fast.ai stuff. And he had a simple heuristic. So he got the data for both competition and had a kind of a 1-0. He didn't release his code, but from what he has written, you can infer what he has done. So he trained it to identify which competition each image could be from. And then he has a way of calculating the confidence intervals, and then he's a way of scaling it down. So, yeah, and also for when there's no landmark. So you identify images that have no landmarks. So this competition, what's good about this method is you didn't use any specific tool, use like geometric information in computer visions or any of those. So it does use CNN all through. So what he had to identify like which image had landmark or no landmark, or which image is came from which competition and which, and then figure out a way of calculating these confidence intervals. So from what he described, so identify the nearest neighbors and the distance between your query images and those neighbors in your distance matrix, and then so take the maximum. So I didn't understand this before, but later I figured it out. So maybe you look that up. So then when you merge this, the merging part is not clear. So because the precedence of arithmetic operations in the computer language, I don't know, is it this over this, or you have to run it and see what it is. So this is also one part. You actually use a concept named metric learning. So this is where from your data, you figure out the metrics that can help you distinguish two distances. So that's where this arc losses came in. So you actually use this in this model, and then the rest was similar to the other one. So this is actually the new thing they introduced. So these are actually designed for identifying human faces, similarity between human faces. So he used it in this competition. And then he identified the way he calculated a trend. He got all images containing different landmarks, choose 100 of them each, took a mean of them. So those served as a centroid of those classes. And then for each vector he has, he compares to those centroids and choose the one with the lowest distance. And then if it's beyond the distance, he matches it as no landmark. So that was what he did. So so this is just Yeah, sometimes when you want to predict a model and there's no loss and there's no label in the neural network, if you have some way of thresholding, you check what gives you the best score. And then, yeah, you can now, because sometimes if there's no label, that's when the entropies are the highest. So because all classes are equally likely. So this is actually how the probability changes, how your what's the entropy changes as your probability changes. So if you're very random, so that's when you have the highest entropy. So in that context, if you have like your one-hot encoded vector that has where everything is likely, so you have values that are pretty much equal across. So if you have a good way of thresholding, you should be able to figure out at that point there's no label. Yeah, so yeah, actually I did a lot of, so when you're parallelizing solutions, figure out if it's processor bound or IO bound. I usually use multiprocessing, parallelize my solution. So there's some, yeah, you can do by model or by data. By data is the easiest because, yeah, you can actually just have batches of the data running on different processes. So, yeah, so this is just like the interleaving of processes describing how those could work in real practice. And how am I doing for time? How much time remaining? Oh, okay. Okay, then, yeah. So these are my summaries, and thank you for listening.